Thank you very much. Thank you for the invitation, and it's a great privilege to speak in memory of Jan Nekovar. I interacted with Jan a few times when he was visiting Tony in Cambridge, and again when he visited London, I think for a term in 2018. And he was always very kind and encouraging. Especially I had a project with Christian Johansson that was related to Jan's work on parity part of BSD, and Jan was very encouraging about this. So I'm going to talk about something cytotape for Bianchi modular forms, which, well, I don't know if you'll see during the talk or not, but some of the ingredients in this talk will be reminiscent of some of the things that Jan used in his work on parity, things like potential modularity. He had some computations with Breuer-Kissing modules and integral p-adic Hodge theory in some of his papers, which will appear at the end of this talk. And of course, things to do with congruences between modular forms appear very frequently in Jan's work. So, yeah, I mean, what I'm talking about doesn't sort of directly relate to Jan's work, but I think there's some kind of thematic connections. Okay. Which is not a surprise given how broad Jan's interests were, as we're seeing this week. So I'm going to state a theorem about compatible systems of Galois representations, which will be joint work with George Boxer, Frank Caligari, Toby G, and Jack Thorne. So to start with, I just need to recall a little bit about the definition of compatible systems of Galois representations, which I'll be using. So that's going to be my first section. So I need some notation, apologies to Matt. So I'll have a number field F, so that's going to be a sort of number field whose arithmetic I'm concerned with. There'll be a coefficient number field M as well. Okay, there'll be a dimension for my Galois representations, and that'll be D. And I'll have a set of finite places of F called S. So those will be the places where my Galois representations are allowed to be ramified. Okay. And of course my compatible system will consist of a bunch of Galois representations. Let me give you a definition. So they're going to be continuous representations of the absolute Galois group of F, indexed by the finite places lambda of M. They'll be d-dimensional, and maybe the coefficients will be in some algebraic closure of the lambda-adic completion of M. As I said, these are going to be continuous representations, and they're going to be semi-simple. Okay, and we'll say this collection of representations forms a compatible system. Unramified outside S. If, so there'll be two kind of key properties. The first is that each of these are lambdas, will be unramified outside S, and places dividing the residue characteristic of lambda. So maybe I'll say they're unramified outside the norm of lambda. Good, and so then we can talk about evaluating these Galois representations on Frobenius elements at places outside this set. So all places in F that are not in S and don't divide the norm of lambda say, yeah, for such a place, when I evaluate this representation on a geometric Frobenius element, it has a characteristic polynomial. Which I'll give a name, P sub Vt. And it will be rational. The coefficients of the characteristic polynomial will live in my coefficient field M. Okay. And it will be independent of lambda, as the notation suggests. Okay, so we have a kind of rationality condition and we have an independence of L condition. So I think if you look in sort of Sayre's book on abelian L-adic representations, this is roughly the definition of compatible system that he gives. But outside the case of dimension 1, it's very hard to prove anything with this definition of compatible system. We kind of, I think Sayre asked the question, do all such compatible systems come from geometry? But we can't prove very much about that without putting some extra conditions on these Galois representations. So that's going to be number 2. Okay, which means we need to introduce some kind of geometricity condition in the sense of Fontaine and Mazur. And maybe the simplest condition to introduce is to say that for almost all lambda, so for me almost all will mean for lambda dividing a rational prime L, and the rational prime L lives in a Dirichlet density 1 set. So this is, you could say for all but finitely many lambda, but it's kind of useful maybe to just have a slightly weaker condition. So for almost all lambda, we'll ask that...
so what is the Dirichlet density 1? Is the L or the lambda?
The L. And so for these lambdas, our lambda will be crystalline. Of course, when you restrict the appropriate decomposition groups at L-adic places, and I won't make it precise here, but when I state the theorem, there'll be a more restrictive condition. Here we should add something like that the Hodge-Tate weights are independent of lambda. So this definition, perhaps a little bit vague, but that will be my sort of working definition of a compatible system of Galois representations. And, well...
Is there then a compatibility with the characteristic polynomial, or also in the, when you classify crystalline?
You could, of course, ask for more. You could ask for a compatibility for the characteristic polynomial of crystalline Frobenius. I won't do that. It's useful actually just to have this weaker condition. But you could, I mean, there are many different choices of definitions of compatible systems. The more sort of stringent you make your definition, the harder it is to produce examples of compatible systems.
So that's why I prefer this weaker one.
I've chosen your representations to be m lambda bar, but just to convenience.
It's for convenience. They're semi-simple, and we've got a rationality statement on the characteristic polynomials of Frobenius. I don't want to say they're really defined over m lambda, but the sort of the isomorphism class is really kind of m lambda rational.
So I think in the function field case, someone proved some time ago that you can do it. That is, if you start, of course, there is the work of Lafort relating those.
Just not to talk.
Yeah, in the function field case, there are very strong results about compatible systems. Yeah, but I'm going to focus on the number field
You
case.
can also change the m lambda bar to m lambda by increasing m in the function.
You can, yes.
Thanks. Okay, that's a definition. Let me talk about some properties I'll want for my compatible systems. So maybe I'll use sort of curly R to denote a compatible system, and I'll say that it's irreducible if the lambda-adic representations are irreducible for almost all lambda, in this sense of almost all that I introduced here.
Can you explain why you request density 1 only and not almost everywhere?
Because, as will come up later, when I have an automorphic representation of GL2 over a CM field, we can often produce compatible systems satisfying this, but we don't know that they satisfy the stronger condition. Yeah, so this definition is kind of adapted to what we can prove at this moment in time. Yeah.
Sorry, and here almost all also means the same?
The same, yeah, lying over a density 1 set of rational primes. Thanks.
And so if I fix the lambda, the crystalline condition is only at lambda or is at all places over L?
It's for all places over L. Yeah. Okay, that's an irreducible compatible system. And of course, my talk will have things to say about relationship with automorphic representations. So I want to introduce the notion of an automorphic compatible system. So we'll say R is automorphic if for all embeddings from my coefficient field to the complex numbers, I can find an automorphic representation, hospital, of GLN of GLs of F. Let's say unramified outside S as well, although we could enlarge the set of ramified primes. And the connection between the automorphic representation and the compatible system is that for places D not in S, these characteristic polynomials of Frobenius can be read off from the Satake parameter, basically the characteristic polynomial of the Satake parameter for the local factor of the automorphic representation. Yes, thank you. D is the dimension of my Gauss representation, and we here have automorphic representations of GLD. Right. So, yeah, of course, same a case of D equals 2 and F equals Q. If I have a cuspidal Hecker eigenform, then Eichler, Shimura, and Deligne constructed one of these compatible systems, maybe for the crystallinity. This was proved by Foltings and maybe Tony. I think Tony as well. Yeah. Okay. And well, if you're just interested in Gauss representations, what's the point of this automorphicity condition? Well, if R is automorphic, that tells us a lot about the L functions of these Gauss representations. This relationship between the Frobenius polynomials and the Satake parameters means that up to some factors at the ramified primes, the L function of pi, standard L function of pi, is the same as the L function of this compatible system of Gauss representations. So the sort of many results we know about automorphic L functions can be transferred to the L functions for these Gauss representations. Okay, and our expectation, maybe following Serre, Langlands, Fontaine-Mazer, and Clauzel, is that if I have an irreducible compatible system, then R should be automorphic and sort of maybe in a orthogonal direction, it should also be motivic. A notion that I won't define, but you probably know what it means for a system of Gauss representations to be motivic. So that's a kind of expectation.
So in this definition of automorphic, is it known? So you need some multiplicity one or some theorem that determines. So suppose, for example, it's
we have multiplicity 1 for GLN, so multiplicity 1 results for automorphic representations are unknown.
and if you know it outside a larger S, you know it outside S, or this is known.
We have strong multiplicity 1 indeed, so it really pins down. Understanding these Satake parameters at all but finitely many V pins down pi precisely. On the Galois side, that's a sort of an avatar of Chebytarev density. But if we understand the Gauss representation away from finitely many places, we've pinned down the isomorphism class of this semi-simple Gauss representation precisely. Okay, that's sort of preliminaries on compatible systems, so now I can state a theorem. So this is with my co-authors I mentioned at the start. Okay, and it's going to be about, well, probably about two-dimensional compatible systems. Okay. What else is it going to be about? So F will need to be a CM field. Okay, this is kind of the limit of our understanding of the relationship between automorphic representations and Gauss representations. We have to kind of restrict to CM fields. Okay, R is going to be an irreducible two-dimensional compatible system. Okay. And we'll now have a restriction on the Hodge-Tate weights. So they have to be sort of parallel. So let's say Hodge-Tate weights really, because we need to take into account coefficients, the labeled Hodge-Tate weights are all zero and m for some fixed positive integer n. So these labeled Hodge-Tate weights depend on a embedding from my local field FV to the coefficient field n lambda bar. And this is sort of a parallel weight condition. It's saying whatever the embedding is, the Hodge-Tate weights are the same, 0 and n. So maybe I'll carry on over here. So that's the kind of setup. I can write the conclusion here. So the first part is a purity result for this compatible system. So R is pure of weight m. So that means the roots of my characteristic polynomials of Frobenius are weight m Bain numbers. Okay. And then next two parts are they're called potential automorphy results. So it means after you restrict to the absolute Galois group of an extension field, you get an automorphic compatible system. So number 2 says there exists an extension of CM fields F primed over F. And if you restrict all of my Garrett notations in a compatible system to the absolute Garrett group of that extension field, then you get an automorphic compatible system.
So can I ask a stupid question?
Of course.
I asked Sasha already, but what if D is 1? Can you say exactly what?
D is 1. Excellent question. Yeah, so with this definition, Serre already, maybe with some transcendence theory results of Waldschmidt, just using number 1, Serre proved very strong results about these compatible systems for D equals 1. So he proved that they are automorphic. They come from algebraic Hecke characters. Yeah, thank you. So D equals 1 is the sort of one case where we have...
Really complete.
Okay, and then you don't need to. Do you need the second
You don't need a second one.
You do. No, you do not. Yeah. Okay, thank you very much.
But you kind of get it.
You get it, exactly. It turns out to be automatic. Yeah, which maybe we expect in general, but we have no...
And do you get yeah, this was why I was asking the question. So and then do you get 2 in the shape you wrote, or for
You get it for
almost all?
You get it for all, like, well, for crystallinity, I mean, maybe there's some ramified places, but you get a de Rham or potentially semi-stable.
I feel that one. Okay, thank you.
Great.
Yeah.
Just to expand on that a bit, is it true that all of the different flavours of the definition with weaker or stronger conditions, you would expect that if you assume the weakest possible condition, actually the strongest condition is true?
Exactly.
It's just that our knowledge doesn't quite match up to that conjecture.
That's exactly it. Yeah.
Yeah. So this definition is adapted to what we can prove, but yeah, as David says, you would imagine this definition is actually equivalent to the same thing with number 2 deleted, but also to much stronger things, to much what you might call a strict compatible system in some references.
Also, just for D equals 1, you don't need to assume anything about F, right?
And veil numbers by convention are algebraic integers or integers outside P.
Algebraic integer.
Veil number, you can either say it's an algebraic integer invertible with some absolute value condition, or algebraic integer, the ring localized at P, so inverting. So
there'll be algebraic integers. These characteristic polynomials will have integral coefficients. Thanks. Okay, we have this potential automorphy statement. So automorphy over some extension field. And then there's a kind of more general statement about symmetric powers of this compatible system. So here I should assume that R is not kind of induced from a quadratic extension of F. I'll just say not induced for short. Then for all positive integers, you have a potential automorphy statement for the nth symmetric power. So for all n greater than or equal to 1, there exists an extension field which might depend on n I can take the nth symmetric power of my 2-dimensional compatible system. That will give me an n plus 1-dimensional compatible system. I restrict to this extension field, and then the result is that that's automorphic as well. This will also be a CM extension. Thank you. Yeah. Okay, cool. So maybe I'll make a couple of remarks on this theorem if the statement is relatively clear. Okay, so we prove purity of some compatible system of Garrett's notations. So traditionally, the way you do that is by applying the Weil conjectures, right? But that's not what we do in this setting, because we don't prove that these automorphic compatible systems are motivic. So that's something that we really don't know in this setting of sort of compatible systems over CM fields. So this is in contrast to the cases where, I'll just write a sort of arrow. So in the cases where f is maybe equal to q, or is a totally real field, I'll say a bit about the history of these results in those cases later. But in those cases, once you produce these once you have these automorphic results, you show something close to the fact that this compatible system is motivic. Not exactly in all cases, but anyway, they're pretty close to being motivic. So we can't apply the Weil conjectures to deduce one. In fact, what we do is follow our idea of Langlands long ago to use number 3, potential automorphy of symmetric powers, to deduce purity. Goes back to Langlands. And the idea is just that if you have weak information about the size of the nth power of a number for all n, then you get rather precise information about the size of alpha. Okay, what I'm writing is just some symbols to, it's like a mnemonic for what I just said, but hopefully the idea is clear. So you get this sort of these weaker bounds on absolute values of Frobenius eigenvalues from the automorphic theory, results of Jacquet and Schleiermacher in this case. And that's enough to deduce purity of the eigenvalues that you started with. Okay. Right. This trick of Langlands, yeah, exactly, went into Delisle's proof of the Weil conjectures. Let me get back up there.
In part 3, could you relax the assumption, like assuming R is not induced?
So if R is induced, then it sort of comes from a compatible system of one-dimensional representations over a quadratic field. And as Helene was asking me about, in the one-dimensional case, we understand things very well. So you can treat that case directly. The only issue is that these symmetric powers won't necessarily come from cuspidal automorphic representations. Once you have n big enough, this compatible system will become reducible, and you expect it to come from kind of Eisenstein series, or you can show that it comes from Eisenstein series.
So is it known in general that automorphic implies purity?
No, you need symmetry.
No.
You need to know the symmetry.
Yeah. So, right. So if we knew that, then we could sort of stop at 2. Right. So in general, for automorphic forms, we have weaker information, like these Jacquet-Schleiermacher bounds I mentioned. But once you know automorphy of symmetric powers as well, you get purity.
And can I ask another small question?
Of course.
If you were believing in the motivicity conjecture,
yeah,
what kind of scheme what kind of variety would you expect here in the rank 2 case?
Good question.
Good question. I don't know. Right, if this Hodge Tate wave M is equal to 1.
You go beyond abelian varieties of specific kind, or whether you stay with one geometry. That's my question.
Right. yeah, I mean, it's quite difficult to construct motives with weights, non-consecutive Hodge-Tate weights. Right? When we have sort of families of motives, a non-trivial family, sort of Griffiths translatality forces the Hodge-Tate weights to be consecutive, something that will come up later, actually. So, yeah, it's quite hard to produce motives whose Hodge-Tate weights have gaps. So I think that's one reason why we just don't know a good way of producing these motives.
Even in much simpler examples like your setting, we
Yes.
already find it very hard.
Okay. So what was I going to say? Yes, we used 3 to prove 1. That was the first remark. Let me do a second remark. As you'll already find in Sayre's book on aladic representations, number 3 here is enough to prove kind of equidistribution results for the Satake parameters or for the Frobenius conjugacy classes. So number 3 because it gives us some results on the symmetric parallel functions. This is following Tate and Sayre. This is enough to give us Sato-Tate equidistribution laws. Okay, so that's the sort of motivation for the title of my talk, but maybe I won't give sort of more details of this here, because I kind of wanted to focus on the compatible systems result, and then later I'll talk a little bit about one ingredient in the proof of this theorem. Okay. But, I mean, in brief, the point is that these potential automorphic results allow us to prove like lots of cool things about these Galois representations. And this idea goes back to Taylor. In his paper on meromorphic continuation of RTL functions. Or, yeah, sorry, meromorphic continuation of L functions in general. Rank 2 L functions, I guess the title is. Okay, and yeah, let me state a corollary. So I think it was Hélène asked whether purity was known for automorphic compatible systems. So it wasn't, but once you have this result, you can apply it. So as a corollary, we get new results about Ramanujan conjecture, which is a conjecture about purity of automorphic compatible systems. So this is a corollary. In the automorphic world. So let me stick to F an imaginary quadratic field, because that's where we have kind of results without an extra assumption. Pi will be what's called a regular algebraic cuspidal automorphic representation GL2 of the Adels of F. This regular algebraic condition means that well, it's due to Clauzel, and it means that pi will contribute to the cohomology of a locally symmetric space for this imaginary quadratic field, for GL2 over this imaginary quadratic field. The coefficients of that cohomology group depend on the infinity type of this representation, and once we move to Galois representations, that infinity type will show up in this Hodge-Tate weight M. So. Okay. Or sort of in more classical language, these pies are kind of generated by cuspidal Bianchi modular forms, which are Hecker eigenforms, and have weight, I think, k at least 2, if you use the kind of classical normalizations for the weights, which are kind of compatible with our normalizations of weights for modular forms, elliptic modular forms. Okay. So that's the automorphic context I'll be in. I'm going to be interested in these kinds of pies. And then the kind of counterpart of the first part of the theorem is that this pi satisfies the Ramanujan-Pedersen conjecture. So that's the Ramanujan conjecture. So that means that the local factors of pi are essentially tempered for all places V. When you translate that in terms of Satake parameters, it exactly sort of matches this purity condition up here. At the unramified places. Okay. Okay, and then no, number 3, because I've skipped 2, but I'm just going to 3 because that comes from number 3 in the theorem. That again is this Sato-Tate equidistribution law. So
the Ramanujan conjecture is only at unramified places, or more?
You can generalize it, but those are actually sort of easier to handle, because if I have a twist of Steinberg, that's actually automatically essentially tempered. The same for a supercuspidal representation. So the sort of crucial thing is to check what's going on at the unramified places. The fact that it's essentially tempered at Archimedean places is what's called Clausel's purity lemma. So let me just write Sato-Tate conjecture for pi. If you're not familiar with sort of these Sato-Tate equidistribution statements, then well, there's a beautiful expository article of Maser called Finding Meaning in Error Terms, which if you haven't ever seen anything about the Sato-Tate conjecture for elliptic curves, I recommend you, well, maybe you shouldn't even wait till the end of my talk, but at the end of my talk, you should go and read Maser's article. Okay, and well, of course, the point of this, the proof of this corollary is that we need to attach to pi a compatible system and then apply the theorem. So, of course, this process of attaching compatible systems to automorphic representations is, the proof of the theorem has to use that a lot, of course, because we're proving that certain compatible systems come from automorphic representations. Let me just recall a tiny bit about the history of this problem. So the proof of this corollary is just that you use a compatible system R pi attached to pi. So the characteristic polynomials of Frobenius for this compatible system match the Satake parameters of pi. And well, the construction of this compatible system has quite a long history, going back to Harris, Soudry, and Taylor. As I mentioned, they're sort of not proven to be motivic. Their construction involves using p-adic congruences, or maybe l-adic congruences, to construct the Gauss representations. Let's see. And then, so that gives you at least a compatible system satisfying point 1 in my definition. And you need to do more to prove that you have some kind of crystalline property for these compatible systems. So crystallinity building on work of Scholzer, Cariani, was only proved quite recently in sort of work with 10 authors, Allen, Caligari, Cariani, Helm, Leihung, myself, Scholzer, Taylor and Fawn. Did I miss? That's 9.
G.
G, Christ, sorry. Don't tell Toby, I'm on video. I knew I should have looked at my notes. Okay, thank you. Toby G was the one, yeah, thank you. Okay, so in this result we proved kind of enough crystallinity to show that attached to this automorphic representation pi, you really have a compatible system satisfying the definition I started with today.
Can I ask a provocative question?
Sure.
Do you really believe this is motivic?
Yeah, maybe not anymore. I don't know. I don't have strong reasons to believe. It seems hard to get a handle on that question.
And this process of construction of API works for which kind of automorphic representation?
You believe it?
Yeah.
Okay.
What do you mean you don't believe in Fontaine?
Well, I don't know anymore. I believe in Fontaine-Langlands, in the automorphicity of its compatible systems, but the motivicness. Okay, anyway, motivicity, I don't know, motivatedness. It was a provocative question, so let's not get sidetracked. Anna, you asked me if there was a more general. Yes, that's right. So we have more general results about Gauss representations for automorphic representations of GLN over CM fields. There's a kind of in fact, for higher dimensional things, you can't quite verify the crystallinity condition at a density 1 set of places. There's a kind of wrinkle there. So in fact, even with that weak definition of compatible system I gave, at the moment you only sort of definitely get compatible systems for GL2 over CM fields. Okay, so this is a bit about sort of the compatible system for GL2 over an imaginary quadratic field. Let me tell you a tiny bit about the history. How long have I got? Ooh, 55. Yeah, tiny bit about the history of this kind of question around potential automorphy. Okay, so I stated this theorem for CM fields. We know much more over, well, when f is rational numbers or totally real. So when this is the history part. F equals Q. You can actually basically remove these potential things. You can just prove that the compatible system is automorphic and that the symmetric power of the compatible system is automorphic as well. So the kind of wrinkle to do with whether your Gauss representations are even or odd, which is essentially handled by Caligari. So let me just say that you can do this without potential. This is a consequence of Caron van der Berger's proof of Serre's conjecture for number 2, automorphy of a compatible system. And then Caligari to handle this even versus odd thing. The deal is that these Gauss representations, you shouldn't be able to get even Gauss representations with distinct Hodge-Tate weights. So I had this condition that m in my Hodge-Tate weights was a positive integer, and Caligari proves under a small technical assumption that basically rules out this compatible system being even. So complex conjugation being trivial. Okay, so that's that and that's that. And then symmetric powers, I guess, there's work of myself with Thorne that proves automorphy without the potential. But of course, there was earlier work that proved the potential automorphy and deduced the Sartor-Tate conjecture without getting automorphy on the nose. Good. And then it's F totally real. Kind of potential automorphy in number 2, that's essentially due to Taylor. I should add Caligari again to handle this odd-even issue. And then number 3 is, again, this work of, maybe I'll write Taylor, Clauzel, Harris, Scheffer-Baron, Barnett-Lamb, G and Geraghty. Okay, it's quite a long story, so I'm inevitably missing some people out, but this is kind of some of the key names who proved a result like number 3 when F is a totally real field. As I mentioned, in those cases, you essentially know that the systems of Garrett notations coming from Hilbert modular forms are motivic. So in these cases, you have quite strong evidence that these compatible systems do come from motives. Let me just put in parenthesis that here the situation is somehow more motivic. Okay. There are still cases there where we don't actually have motives, but okay. Okay, and more recently, this 10-author paper that I already mentioned there we do the case where this Hodge-Tate weight M is equal to 1, and F is a CM field. So in the last kind of 13 minutes or so, I'll tell you why generalizing beyond m equals 1 required some more work, and sort of at least one of the key new ingredients we have for our new theorem. Okay, so what's the sort of strategy that underlies the proof of all these theorems? Well, very briefly, let me ignore the symmetric powers for now, so we'll just do the two-dimensional compatible system. And what we want to do is find a chain of congruences connecting our compatible system, may be restricted to an extension field of F, to an automorphic compatible system. And then once we have this chain of congruences, if we've set them up correctly, we can then propagate this automorphy through the chain using automorphy lifting theorems. So how do we build these congruences? This is actually very much like the question Jacob Zinnerman raised in his talk, where you have a fixed finite Galois module, and you want to find maybe an elliptic curve that realizes that fixed Galois module. So you do that by looking for rational points on a certain moduli space. So one of the examples Jacob was talking about, if you look at the genus zero modular curve x5 and you found a rational point, a non-cuspidal rational point, then that gives you an elliptic curve whose 5 torsion has a certain Galois module structure. So that's an example of building one of these kinds of congruences. Okay. So if you're on a sort of more general moduli space, you don't expect to be able to find rational points, but if you allow yourself to make some kind of extension, then of course it's much easier to find points valued in that extension. So that's what's kind of going on here. We have to allow this extension so we can find f-primed rational points on a certain moduli space, and then we can ensure certain local conditions using a local global principle of Moret-Bailly. Okay, so that's about finding the chain of congruences, and it uses some family of varieties, the Dwork family in this case. And as I mentioned before, you have this restriction coming from Griffith's transversality, but in this family, you're going to have, your motives will have consecutive Hodge-Tate weights. So that's the sort of problem with trying to go beyond m equals 1. We can sort of, for sure we can't find an elliptic curve anymore whose Hodge-Tate weights will match the Hodge-Tate weights of our compatible system of Galois representations. And there's something called the tensor product trick of Harris that kind of fixes this. So we take our Hodge-Tate weight 0m representation and we tensor with something whose Hodge-Tate weights are consecutive, ranging from 0 to m minus 1. And if we do that, suddenly we have now a 2m-dimensional compatible family of Galois representations whose Hodge-Tate weights are consecutive. And then we can try and build the congruences using moduli spaces for those tensor products. Okay. So that's at least one part of the strategy. And basically, the more complicated this bit of the strategy gets, the sort of stronger your automorphy lifting theorems need to be. So one of the sort of main ingredients, new ingredients in our work, is to kind of strengthen the automorphy lifting theorems that apply in this kind of context. So I'll spend the last few minutes talking about what we need to do that. So I won't give you a sort of statement on automorphy lifting theorem. I just want to tell you about a couple of ingredients. Thank you very much. So in our setting, we need better automorphy lifting theorems to carry out this strategy. And, well, there's at least 2 ingredients we need to do that. So one is a local global compatibility result that I proved with Arne Cariani. In this kind of setting. I've forgotten how to spell at this point in the morning. Compatibility. Okay. So we had some new results on local global compatibility, which we applied to prove modularity of certain 2-dimensional Galois Gauss representations, like those coming from elliptic curves over CM fields. And they're useful in this situation to prove stronger modularity lifting theorems, which will apply to these 2 m-dimensional Gauss representations. So that's one ingredient. And then the second is just a purely local ingredient about Galois deformation rings. Which I'll explain in the last 5 minutes. Okay, so now I'm in a local setting, so K will be a p-adic local field. I'm doing sort of Galois deformation theory, so I fix a residual Gauss representation, rho bar, of the absolute Galois group of K. It's d-dimensional again, it has coefficients in some finite field K. We're in the sort of PP situation, so we're looking at p-adic representations of this p-adic Galois group. And then, because of our setup, the kind of Galois deformation ring we're interested in is what I'll call R Cris 0. So this is a complete Noetherian local algebra over the Witt vectors of the finite field K. And it classifies lifts of rho bar which are crystalline with consecutive Hodge-Tate weights, so 0 to d minus 1. So this was constructed by Kissin. And Kissin proves very strong results about the generic fibre of its deformation ring. When you invert P, you have something regular. That's a very important fact in the geometry of these deformation rings. But what we needed to prove was something about the special fibre of its deformation ring. It's something that's a bit harder to access.
So the regularity is when you invert P, or?
Yes, when you invert P, it's regular. That's right. But understanding the geometry of the special fibre of this deformation ring is, for example, tied up with the Breuil-Mazard conjecture. So, yeah, now I can state this local theorem. If I look at, well, let me assume P is bigger than the dimension D. Okay. So that means P is large compared to the Hodge-Tate weights of the representation. That's important. But we are allowing ramification in K, so this is not kind of somewhere where we can apply Fontaine-Lefebvre theory. And the statement is just that if we take the special fibre, so we reduce modulo P, uniformizer in WK, then we get something which is generically reduced. And this fact, I mean, doesn't look at all related to the sort of global picture I was talking about earlier, but this kind of property of a mod P fibre of a deformation ring is crucial for carrying out Taylor's method of avoiding Ihara's lemma. So this gets used in what's called Ihara avoidance, for those who are familiar with the sort of automorphy lifting literature.
I'm sorry.
Yeah.
So the assumption on the residual representation was irreducible or just general?
General. Continuous. Yeah. Thanks. Okay, that's the theorem.
Is generically reduced even if it's not irreducible?
Mm-hmm.
Okay. And not so much simple?
Yeah, in fact, well, let me say one sentence about the proof. It uses sort of amazing fact, thanks to Emerton and G's construction of a moduli stack of Gauss representations and their theorems about it. It's the amazing fact that you can try and prove these statements by, you can vary rho bar and restrict to a kind of, maybe a generic family of rho bars. So you can sort of reduce looking at generic rho bars, which in fact are precisely fully reducible but non-split representations. So that kind of case you're asking about is exactly what you have to move to in order to prove this result. So these rho bars are fully reducible. So they're extensions of characters, but they're non-split extensions of characters. And what we prove is, for a suitable definition of generic rho bar, this deformation ring is actually regular in that case. It's formally smooth over WK.
So maybe just the arrow doesn't mean that we prove this. I guess the arrow just means that we give you the tool so you can.
Exactly, yes. That's what I tried to say, and the arrow tried to abbreviate that. But yeah, exactly. But, you know, yeah, it's something that I think, in fact, I remember a conversation with Jan Nekevar about the Emerson G stack, and he was certainly very excited by this thing that felt like science fiction maybe 10 years ago, that you could, yeah, understand Gauss representations in a way that by moving the rho bar to kind of prove results. I think this is, yeah, super cool.
And why P is bigger than D?
Why is P bigger than D? This is sort of a technical reason to do with integral p-adic Hodge theory and relating Breuer-Kissing modules and Broglie modules and lattices in crystalline representations. So this assumption appears in a theorem of Tonglu that we use on a conjecture of Broglie.
Then maybe is this theorem possibly?
If D is bigger, if you don't have this inequality, I think that's right. I think that actually you don't expect this result. And I think there's an example written in our paper actually that sort of, at least, or a heuristic at least, illustrates why some assumption like this is probably necessary. Okay, that's it. Thank you very much.
So are there some more questions from the speaker?
Yeah, I did not get the last step. So the last step, prove on the rho bar, and then you said something magical, and then you said you were done. But I did not get it.
So what we do is we prove that for many rho bars, this crystalline deformation ring is actually formally smooth. And we do that by proving that it coincides with the ordinary deformation ring. So we prove that all of these weight zero crystalline lifts must be ordinary if you have a suitable rho bar. And then you can, it's not so hard to prove that the ordinary deformation ring in many cases is formally smooth over the Witt vectors. So, well, okay, so now for those generic rho bars, we have a formally smooth integral deformation ring. So for sure its mod P fiber is reduced. And then, again, using the Emerson G stack, you can use that to prove that the whole sort of crystalline weight zero mod P Emerson G stack is generically reduced. And now you specialize back to any rho bar.
And you get generic reducedness for that.
Is there any hope of taking something that isn't on GL2 to start with, say and some pi on GL3, and then proving sample state essentially.
Well, there are potential automorphy results due to Lieh Chan, whose work also plays a role in our work. So I should mention those, but that's just for the sort of the GL3, the three-dimensional Gauss representation. If you want to then try applying some Langlands functoriality, the problem is that you're going to, basically, I think in every other case, you're going to move into a situation where you have non-regular Gauss representations. So then all the sort of methods for automorphism theorems break down. So yes, we're kind of lucky that symmetric powers of regular Gauss representations remain regular. That's good news. In more general situations, this breaks down. So it's somehow, yeah.
So is this deformation ring local complete intersection?
I don't know.
No, but you said that you prove generically reduced by.
So I think Oak is asking why there are no embedded points.
Okay. There could be embedded things. Okay. There could be embedded things only generically.
Yeah, it doesn't. Yeah, it's not excluded by.
It doesn't exclude embedded primes. That's right.
But you know the dimension of the components.
Yes.
Yes. Yes, I do. Yes, I do.
I guess with that, Toby and I showed that things are equidimensional.
Right, but there could be embedded points, right?
Yeah, I guess.
For Helmholtz from B happens, right? So I think it's quite, it would be bold to conjecture that it doesn't happen in this case.
Since you mentioned L a bit different from P, Taylor proves kind of results like this for deformation rings in the L different from P case. And the proof is conceptually similar. There's a sort of moduli space of L parameters where the residual parameter can move. And then you take a complete local ring at the parameter you're interested in and show that that's generically reduced by showing generic reducedness of the global moduli space.
But to answer, in that case, it can be non-complete intersection. In the L different from P.
So is it a modular space of representation or of pseudo character? I mean, no.
R rho bar is a moduli space of lifts, frame deformations.
Frame deformations.
Yes. I mean, the G stack is a moduli space of the gamma.
Okay, so let's sign this security.